I've made several videos on photonic chips on this channel. Germany's photonic breakthrough, China's glass chip, acatonics, and more. And in every one of those videos, the underlying premise is the same. Light is faster than electrons, photonic chips are coming, and when they arrive, they're going to change AI hardware fundamentally. That's correct, but if you've been following this space for more than a few months, you've probably noticed that the breakthrough always seems to be 2 to 3 years away. Lab demonstrations are impressive, but production chips that you can actually order and deploy at scale, still rare, still expensive, still limited. So I want to explain the 5 specific reasons they keep not arriving. When you manufacture a silicon chip, you're working with a process that's been refined for 60 years. The yield rates, the percentage of chips that come out working correctly, are well understood and well managed. TSMC knows within a small margin exactly what percentage of a wafer will be good before they start. Photonic chips introduce components that silicon manufacturing wasn't designed for. Waveguides, the tiny channels that guide light through the chip, modulators that encode data onto light signals, photodetectors that convert light back to electrical signals at the output. Each of these has to be fabricated with tolerances that are extremely tight because small variations in the geometry of a waveguide change how light propagates through it. Unlike digital circuits, where a transistor is either on or off, photonic components are analog. A waveguide that's a few nanometers too wide or too narrow doesn't fail completely. It drifts. The signal degrades in ways that are hard to predict and hard to detect until the chip is already packaged and tested. The result is yield variability that the industry hasn't fully solved. Photonic wafers have roughly 39% yield variability compared to standard CMOS processes. Fabrication process steps are about 55% more complex. Every extra step is another opportunity for something to go wrong. This isn't unsolvable. Yield problems in electronics were once considered unsolvable too, but it means photonic chips can't yet be manufactured at the cost per unit that makes them commercially competitive for mass deployment. And until yield improves, the economics don't work at data center scale. Light doesn't spontaneously appear inside a chip. Something has to generate it. In most photonic architectures, that something is a laser, and lasers are where the physics gets inconvenient. Silicon, the material the entire semiconductor industry is built around, is terrible at generating light. It's a poor light emitter due to its indirect bandgap, so you can build your waveguides and modulators in silicon, but you need a different material for the laser source. Usually indium phosphide or gallium arsenide, compound semiconductors that are excellent light emitters but don't integrate easily with standard silicon fabrication processes. This is called the laser integration problem. You're essentially trying to marry 2 different manufacturing traditions: silicon CMOS for the electronics, 3-5 semiconductors for the lasers on the same chip at the same scale with the same yield requirements. The approaches being used include bonding prefabricated laser chips onto silicon photonic wafers, which adds packaging complexity and cost, or growing 3-5 materials directly on silicon, which is extremely difficult and still at early research stages for production quality. Every photonic chip that needs an on-chip laser is carrying this problem. Some architectures avoid it by using an external laser source, but then you have alignment requirements and coupling losses between the external laser and the chip that introduce their own complications. Photonic computing is inherently analog. When light passes through a photonic component to perform a computation, a matrix multiplication, an activation function, the result is an analog signal, not a clean digital 0 or 1. A continuous value that can drift based on temperature, on the age of the component, on tiny variations in manufacturing. For AI inference, this matters because neural networks require a certain level of numerical precision to produce accurate outputs. If your photonic chip is performing matrix multiplications and the analog result drifts by a few percent because the chip warmed up during operation, your model starts producing wrong answers. Electronic chips handle this by operating digitally. Every value is snapped to a discrete level. Errors don't accumulate. Photonic systems need additional circuitry to periodically recalibrate, to monitor signal quality, to correct for drift. That circuitry adds complexity, cost, and ironically requires power, which erodes some of the energy efficiency advantage that photonics is supposed to deliver. Some workloads tolerate reduced precision well. AI inference on certain model architectures can run at 4-bit or 8-bit precision with acceptable accuracy loss. But maintaining even that level of stable accuracy across temperature variation and operating time in an analog optical system is harder than it sounds, and it's an active area of research rather than a solved problem. I covered the CUDA moat in a previous video. The short version is that Nvidia's real competitive advantage isn't the hardware, it's 18 years of developer tooling, libraries, and accumulated knowledge built on top of CUDA. Photonic chips face this problem in a more extreme form than even Intel or Tenstorrent. When you move a workload from an Nvidia GPUs to an AMD GPUs, the programming model is similar enough that migration tools exist and developers can adapt. When you move a workload to a photonic chip, the underlying computational model is different enough that existing software doesn't transfer at all. There are no widely used compilers optimized for photonic hardware. There are no debuggers, no profilers, no established workflows. The engineers who understand both optical physics and machine learning well enough to build these tools are rare. The talent shortage in integrated photonics is consistently cited as the most pressing constraint facing the industry. Every company building photonic AI chips has to build their own software stack from scratch in parallel with building the hardware. That doubles the engineering challenge, and unlike hardware, software ecosystems take time to mature regardless of how much money you throw at them. You need developers to use it, find the edge cases, write the tutorials, answer the Stack Overflow questions. That process takes years. This one is the most counterintuitive, even if you solve manufacturing yield, laser integration, analog accuracy, and software. You still have a fundamental physical constraint that limits how much of photonics' theoretical speed advantage actually reaches the end user. Data has to get into and out of the photonic chip. At the boundary of any photonic system, signals have to be converted between the optical domain and the electrical domain. Your memory is electronic. Your processor coordinating the system is electronic. The network interfaces are electronic. Light can move data at extraordinary speeds inside the chip, but at every interface with the outside world, you need an electro-optical converter, and those converters have bandwidth limits, add latency, and consume power. For workloads where the computation is the bottleneck, where the chip is spending most of its time doing math, photonics' speed advantage is real and meaningful. But for many real-world AI workloads, data movement is the bottleneck. The chip is waiting for data. And if the interfaces that feed data into the chip are still electronic and still limited by electronic bandwidth constraints, the photonic speedup is partially offset by the I/O overhead. In many workloads, this I/O overhead dominates the total energy budget. You end up with a fast optical core surrounded by slower electronic plumbing, and the system speed is determined by the plumbing. This is solvable. The direction the industry is moving is toward co-packaged optics, where optical I/O is integrated directly with compute chips to reduce these interface penalties. But it's a years-long engineering program, not a feature you add in the next chip revision. None of these 5 problems are permanent. They're engineering problems, and engineering problems get solved. Yield variability is improving every year as fabrication processes mature. Laser integration is being attacked by multiple research groups with different approaches. Analog accuracy issues are being addressed through better calibration systems and hybrid digital analog architectures.